Hey guys, in this video I'm going to talk about what happens if you have more than one object in a system and they are coupled, meaning that they are interacting with each other. These are often called internal interactions because they're not interactions with anything outside of the system. Specifically, that means that although the momentum of the individual components of the system may not be conserved, the momentum of the entire system may still be conserved because these are interactions which are not external. They are only internal to the system, so the system's momentum may remain conserved. So let's start with a specific example of this. Here I have three blocks, A, B, and C. They're sitting on some kind of surface, and let's take the surface as very slippery so we have no friction. If A, B, and C are in my system, I have three objects in my system. The way that I've drawn it so far, A, B, and C are not connected in any way, and therefore they are not interacting with each other, and we have no internal interactions. But let's say I move block A so that it is actually in contact with block B. Then we have an interaction between block A and B, and we have an internal interaction in the system. Block C is still doing nothing, so not every object needs to interact with any other objects in the system. You can have pairs of objects that interact and other objects which do not. So we need a way of describing this interaction. Well, it's a contact interaction because it happens at the surface. So the way we'd like to describe that is as a normal force. Normal forces act perpendicular to surfaces, and that's exactly what this force is doing. The contact surface is here, and block B is pushing that way on A, block A is pushing that way on B, perpendicular to the surface. So I'm going to draw in the action of B acting on A. I'm going to call it Fn for normal force, and then I want a special designation so that I know this is B acting on A, so I'm going to write BA for B acting on A. Of course, we know from Newton's third law that for every action there's an equal and opposite reaction, so the action of B acting on A causes another force of A acting on B, which I'm going to call Fn, and then just switch the order, A acting on B. There's a mathematical relationship that I can write between these two forces if I write them as vectors, like so, which is saying that as a vector, the vector which represents the interaction of A on B is opposite in direction, which is denoted by that negative sign, and equal magnitude to the force which goes from B to A. And actually, this is a statement, the mathematical statement of Newton's third law. So I can use this statement to help me write my free body diagrams. So I'm going to start with a free body diagram for block A. So here's my dot that represents the block A. The block has some mass, so I'll just write it Fg sub A to represent the gravitational force on A. The floor is acting on A, pushing up on it, so I can write that, let's say Fna. And then I need to include the force of B acting on A. That's this guy, because that's the one that's acting on the free body diagram I'm trying to draw. So if I copy that over here, it looks like it's about that big, Fn B on A. Want to do the same thing for the block B. Block B looks bigger than block A, so I'll make the gravitational force a little bit bigger. FGB, that's going to make the normal force a little bit bigger. FNB. And now I should say, okay, do I have any other forces on block B? Well, if I didn't know anything, I might say no. But every time I write one of a Newton's third law pair of two objects that are in the system, I know that there is another force exactly like this on the other object. And it should be directed in the opposite direction, F, N, A, B. So even if I didn't have this nice little picture over here of these two forces, as soon as I wrote FNBA, I know that somewhere there's another object that has a force, FNAB, acting on it, and it's block B. So that demonstrates the two free body diagrams of blocks interacting in a system like this. There's another common thing we're going to see when we study coupled objects in the physics lab, and that is objects not just resting against each other like this, but actually attached to each other, for example, by strings. So I'd also like to do a quick example of two blocks connected by a string. So here are my two blocks, A and B, and I'm going to draw a string in between them to represent them being connected by a string. So take the first block. Let's say block B is pulled to the right. So that means block A is going to feel a force from the string on it, and I'm going to call that a tension because that's the tension of the string acting on A. I'm going to write B acting on A. Now maybe I really should write FT string acting on A, but we're going to shortly see that it doesn't matter if you think of the string as being here or the string as being not here. The string is just transferring the force between A and B. So if I go over to B, B feels a string tension FT on A to B. So the next thing we need is a simple fact about strings, which is that the tension on a string is constant over the entire length of the string. So across this entire length, the tension on the string is exactly the same. So what that means is that these two forces right here have to be equal to each other. And actually, to be absolutely careful about it, I'll just write as magnitudes because, of course, they are acting in different directions. But as magnitudes, the tensions will be exactly the same. Now, that's a statement of Newton's third law, but it also means that we can treat this string as basically being non-existent. It's just a connection between A and B. And it doesn't make a lot of sense to talk about A acting on the string and the string acting on B if the tension is all constant throughout the whole thing. So it turns out the reason the tension is constant is a little bit outside what we cover in class, but it has to do with the fact that the string is massless. So if we had a massive string, it wouldn't be directly horizontal like this. It would be sagging in the middle. And so you would have another force, Fg, of the string acting in the middle, and this would no longer be horizontal, and you'd have to balance the force of gravity against the force of the tensions. Not a really hard thing to do, but we usually take our strings to be massless so we don't have to worry about those small kinds of effects. When you have massless strings, the tension is constant over the entire length of the string. And now we can continue with the same kind of analysis that we did in the previous case. I just want to point one other thing out. Although we're talking about using Newton's third law to evaluate the forces between objects which are interacting in the system, we can also say something about the position, velocity, and acceleration of two objects in the system without really doing too much work. So let's consider what happens to B if we pull on A. Well, if we pull on A this way, let's say we pull A such that it has a velocity, a constant velocity of 1 meter per second. Well, if this string doesn't stretch at all, which is normally part of the assumption that goes into these things, then B has to move at the exact same speed that A does. Now, you can prove this mathematically, but for our purposes, it's fine to sort of see that that should happen. Pull A at 1 meter per second, B obviously has to also move at 1 meter per second. So the speeds, VA and VB, are equal to each other. We can say the same thing about the accelerations. If this A is accelerating at 10 meter per second squared in this direction, then B will obviously be accelerating the same way. If you want to prove that mathematically, it just requires taking a derivative of these things, but it's also very easy to see intuitively that the acceleration of A will be equal to the acceleration of B. And before going on, I want to mention that everything here, this part as well as the tensions, is really reliant on how you set this problem up. If I pull A this way, B comes with me, and all this stuff is true. If I pull B this way, all this stuff is also true, because A comes with me. But if I push B towards A, then the string loses its tautness, and it becomes loose, and then the string does nothing. The string essentially drops out of consideration. So you have to be a little bit careful when you set these problems up that you don't break the conditions that you set. These are completely true as long as you pull A that way or B that way. So the last thing I have to mention about coupled motion is pulleys. So pulleys in physics only do one thing. They just change the direction of a string and therefore its tension. Now, just like for the string case, that's because the string was massless. In the pulley case, that means that the pulley is massless, but also frictionless. And that's just because if you had a massive or a frictionful pulley, it means that when you pull on one side of the tension, the pulley might not start moving immediately. You might need to pull with a certain amount of force to get the pulley moving, and that might violate this condition up here of the tension being constant over the length of the string for massless strings. So let's try to talk about that in a little bit more detail. So if I have a pulley, which is massless and frictionless, and I have a string over the top of the pulley, and I pull on the string with the tension T, it means that on this end, there is a corresponding tension T because the tension is constant over the entire length of the string. The pulley has effectively changed the direction of the string and therefore the direction of the tension, but it hasn't done anything about the tension being constant over the length of the string. Now, if this pulley was, say, had some friction on the ball bearings, maybe you couldn't pull hard enough to get the pulley to move. And if you couldn't pull hard enough to get the pulley to move, you would be pulling harder and harder on this end, but there would be no tension in this end. So if a pulley has friction or has mass, the string condition fails, and we need to move on to other considerations like energy or angular momentum in order to solve the problem. But for our purposes, the major job of the pulley is to change the direction of the string and its tension force. All right, great. Well, this has been an overview of coupled objects for the purposes of determining the motion of objects in systems. We're going to get some practice with this next class, and we're going to solve some problems involving strings, pulleys, and blocks being pushed on each other and stacked on each other, and all sorts of combinations. All right, great. Thank you for watching, and I'll see you in class.